Hi and Assalamualaikum. We are from Group 16, consisting me, Mariam, Sabrina and also my Sarah.
We are going to conduct an experiment of 3-point bending test.
And the materials using is wooden pencil.
Let's go!
Hi and Assalamualaikum everyone. My name is Siti Mariam Hidayah binti Muhammad Yusof, matrix number 231341. Now I will be presenting about our experiment setup as illustrated in the slide. For this study, the standard pencil was selected as the material for the experiment. To ensure a stable and controlled environment, we have selected chairs as the supporting structure, while cable wires and shoelaces were employed as feet supports to secure the pencil's position. The loading mechanisms consisted of a gallon water bottle into which water was gradually added. This method allowed us to apply precisely controlled load using the weight of the water to observe the pencil's bending behavior and strength characteristics under increasing stress. Based on our observations, water was added in increments of 550 ml as shown in this slide. The increase in volume resulted in measurable deflection of the pencils. This indicates clear bending behavior under the applied load. During the initial stage, deformation occurred gradually without any signs of failure. With an initial specimen length of 150 mm, we observed a maximum elongation of approximately 3 mm. This specific data point confirms that the pencil was experiencing elastic deformation during this phase of the experiment. The experiment concluded when the volume reached 6.38 liter, at which the point of pencil underwent a complete fracture. This result indicates that the material reached its highest bending moment at this load. The sudden nature of the break signifies the transition from elastic deformation to a brittle failure. This confirms that the material had exceeded its ultimate strength. Moving on to the quantitative analysis of our experiment, this slide presents the stress-strain data table recorded during the loading process. The specimen had an initial length of 150 mm and a calculated cross-sectional area of 1050 mm squared. We conducted the test using a control load increment of 550 ml, which resulted in a total of 13 recording steps. As we observed the data, the load was increased from a baseline of 0 Newton to a final total load of 62.588 Newton. Throughout these increments, the specimen exhibit a steady increase in elongation, reaching a total of 3 mm. This resulted in a final specimen length of 153 mm or 15.3 cm. Moving on to the stress-strain graph. The stress-strain graph shown here visually confirms that the material's behavior under tension. By plotting the stress-strain graph, we observe a consistent, nearly linear line. The stress value reached a maximum of 0.06 megapascal at a strain of 0.02, just before the point of fracture. This linear relationship is significant as it defines the elastic modulus of the pencil material, demonstrating that the specimen was effectively resisting the applied load until it reached its ultimate strength limit.
From the stress-strain graph, we can observe a linear relationship between stress and strain from the beginning until fracture. This shows that the pencil remains in the elastic region throughout the loading process and followed Hooke's law, where deformation is proportional to the applied load. There was no change in slope or curve in the graph, which means no plastic deformation occurred before fracture. This behavior is typical of wood-based materials, which often fail in a brittle manner. So next is Young's modulus, which represents the stiffness of the material. From our experiment data, the maximum stress was 0.06 megapascal and the maximum strain was 0.02. Using the formula E equals stress over strain, we calculated the Young's modulus to be 3 megapascal. This low value indicates that the wooden pencil has low stiffness, which explains why we observe noticeable deflection even under small loads. In terms of yield behavior, no yield point was observed in our graph. The pencil fractured immediately after the elastic region without showing any permanent deformation. This confirms that the material behaves as a brittle material rather than a ductile one. At the maximum load of 62.588 newtons, the stress reached 0.06 megapascal and the pencil fractured suddenly. This indicates the ultimate strength and failure point of the material. The fracture occurred at the region of maximum bending, which is typical for wood under flexural loading. Finally, in terms of energy absorption, the pencil showed moderate resilience as it stored elastic energy before failure. However, the toughness was low because there was no plastic region and the area under the stress strain curve was small. This explained the sudden and complete fracture we observed.
Assalamualaikum, my name is Nurmai Sarah binti Mat Sazali, metric number 230990. I will now present about the lifelong learning that we gain from this experiment. First, the ability to convert theoretical knowledge into reality, where we have to first visualize how the material tested will behave during the experiment. This is to ensure that the results will be identical as the theoretical outcome. Next, creative problem solving, which is acquired during the experiment designing process, where we brainstorm an accessible load system for the experiment. Third, mitigating experimental error, where we acknowledge that the dynamic loading effect can be controlled by the flow rate of water. Lastly, transferable skill is obtained by building the ability to conduct a valid test in environments where specialized laboratory equipment is unavailable. Next, comparison with modern technology. Modern technology conducts 3-point bending tests using universal testing machine. With the availability of digital image correlation, modern technology can provide a full stress strain curve and visualize the strain distribution along the whole specimen. Conversely, our experiment is only able to identify its gross failure and observation at a singular snap point. Some of the critical evaluation gain is that the FSC wood is anisotropic and orthotropic, making it stronger when tensile stress is parallel to the grain. The failure is due to the tensile stress that exceeds its modulus of rupture. In engineering application, it is a sustainable material used in civil construction, but it is limited to high humidity environment and engineering applications with multi-directional stress.